just wanted to look at practice one together as a team. We're going to be looking at the first problem, and it's a clock problem. And you can see that when you get the actual project one, there's a variety of clock problems. So we're going to do the first one. Estimate the measure of the angle found by the minute and hour hands of a clock at 4:20. Okay, so what do you think? Have you guys started to work on that? 4:20, 4 o'clock would be one thing, right? 4:20 is a little trickier, right? How did you do it?
Well, I looked at the clock at the circle. You know, the circle is 360 degrees. And then what I did after that is I broke it down into quarters, which would be 90 degrees each.
Okay.
And then again, I looked at between 4 and 5 o'clock, and that would be 30 degrees.
Okay, how did you get from 4 to 5 is 30 degrees?
Well, because between example 12 and 3 o'clock, if you want to get to 90, it's 30 plus 30 plus 30, you're going to get 90.
So this is 90 degrees, right?
Yeah, that's 90.
So each hour is actually 30 degrees.
Yeah.
Okay.
And then you're looking at 4:20, which is 1/3 of an hour, so that would be 10 degrees.
Okay, so let me draw 4:20 real quickly for the visual learners in us here. This is 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and so we're looking at the time for 4:20. Okay, so it's not halfway between 4 and 5, but it's part of the way through between 4 and 5. Probably the easiest one to start. We're going to probably start by drawing the minute hand, right? Where would the minute hand be pointing? The minute hand, not the hour hand. It's 4:20. It's going to be pointing to the 4. Okay. So there we go. That one's easy, right? It's 4:20. Okay. But 4 has started at 4 o'clock and it's been sweeping out. How much of an hour? 1/3 of an hour, right? So 20 minutes is, 60 minutes is an hour. So 1/3 of the hour. So it's traveling, in an hour, it's traveling from 4 to 5, right? So it's traveled 1/3 of that distance. So I'm going to just draw it in here, about 1/3 of the distance. Okay? And as we just said, the whole distance from here to here is how many degrees? 30 degrees. So if I've swept out 1/3 of that distance, how many degrees is right in here? 10 degrees. Does everybody buy that? So this is 30 degrees for a whole hour. So 1/3 of the hour is about 10 degrees. Okay, it's hard to see that. Let me just put a little arrow and draw a little bigger. Okay, so in here is an angle. It's real small. It's about 10 degrees. Okay, so we were asked what's the angle between the hour hand and the minute hand, and the answer is 10 degrees. Notice we had no problems like this in class, in the homeworks, in the quizzes, practices. Okay, so what am I doing? I'm actually taking the things that we learned in class and applying them to real world situations. Okay, so that's what the project questions are going to look like. Because it would be, especially since it's take home, it would be really boring if I just asked you questions that we went over in class. So I'm actually trying to ask you a little bit something different using the things that you learned. Any questions on number 1? Pretty simple. So each one you've got sort of like a puzzle, and you want to figure out how many degrees are there between the minute hand and the hour hand. Okay. Number 2, Find the sum of the interior angles of a decagon, 10-sided object. Okay, so let me erase and let's take on a decagon. How many sides in a decagon? So it's a 10-sided object. How do you do the sum of the interior angles for a decagon? Okay, so we always, when we looked at the pattern, we found that you always subtracted 2. Why would you subtract 2 vertices? It's sort of like, yeah, you're not going to be able to do triangles with the adjacent vertices, and then you've got the rest of them. Oh, actually, I'm fibbing. You can't have a diagonal with yourself or with your two neighbors. So you actually get n minus 3 divisions. But if I divide an area in n minus, well, I mean, if I divide something, if I take any area and divide it twice, how many regions do I have left? I know this is, okay. If I divide a region twice, I get how many regions? 3 regions. So I only get 1 more. So actually, I can't do a diagonal with myself or my two neighbors, so 3 vertices are taken out. I can do, so for example, let me get very practical here. Let's take a hexagon. Okay, so I can't do a diagonal with myself, and I can't do a diagonal with my two neighbors, but I can certainly do diagonals across the object, hence the name diagonal. Okay, and so I've only got 1, 2, so this is a hexagon. I've only got 3 diagonals that I can draw, but once I draw 3 diagonals, how many regions have I formed? 4, because I sliced it 3 ways, and it gives me 1, 2, 3, 4 regions. Okay, so it ends up being n minus 2 in every case. And this one was 6, and I had 4 triangles. In that one, it's 10, so there's going to be 8 triangles. So 8 times 180 is what? 1440. So this 1440 is the sum of the interior angles of a decagon. Explain why a regular decagon does not tessellate a plane. What does it mean to tessellate a plane? These are tilings. So, for example, I can tile a plane with rectangles. But notice at every point where there's an intersection, how many, let's say they were rectangles, how many degrees is this angle? 90, 90, 90, 90. So when we go a full circle, it's 360 degrees, right? And everything's cool when it adds up to 360 degrees. Triangles would work the same way. If I did a triangle, let me see. Suppose we did a bunch of triangles coming together at a point. I can tile a bathroom floor with triangles. And the reason is, especially if these were equilateral triangles, I get 60 degrees here, 60, 120, 180, 210, 270, I mean 60, 120, 180, plus 60 more is 240, plus 60 more is 300, plus 60 more is 360. So every time I do that, and it works out perfectly, it's going to be 360 degrees. But what happens if I put a pentagon, a bunch of pentagons together? It actually doesn't work, because the pentagon is n minus 2 would be 3 times 180. It's 540. When I divide that by 5, if it's a regular pentagon, each angle is 108 degrees. So I bring one 108 in, I bring another 108 in, I bring a third 108 in, and how many degrees am I up to? 108 and 108 and 108. 324, that's not going to work, is it? Okay, so if I actually put 3 pentagons together, there's a gap. If I try to put a 4th one in, I'm way over 360. So not every shape can tessellate a plane. It has to add up to 360 degrees. So a decagon has 1440, and it has 10 sides. So what's the, if I had a regular decagon, what's the angle for each angle? How many degrees is it for each angle? 144 degrees. So what I do is I bring in one angle is 144. If I bring another one in, how many degrees is that? 288. I try to bring in, this isn't drawn the scale, but I try to bring one more in. 288 plus 144 comes out to 12, carry the 3, 432. Okay, it's not going to work. Either 3 is going to be, well actually 2 is going to be too small, and 3 is going to be too large. So it turns out that there is no, it's not going to tessellate a plane. So when I ask a regular polygon whether that tessellates a plane, the question is, can I put all of them together on a point and add up to 360 degrees? Okay. Explain why a combination of octagons and squares tessellate a plane. They're regular octagons and regular squares. Well, let's take an octagon. An octagon has how many sides? 8 sides. So how many triangles? We subtract 2, right? So it's 6. 6 times 180 is what? 1080. Okay. 1080 divided by 6. Everybody see what I'm doing here? 1080 divided by 6 turns out to be what? 8, excuse me. Divided by 8, thanks. What do we get for an answer? Get a calculator? $135, which sounds pretty funky, okay? And a square is, how many degrees is each of the angles in a square? 90. So if I put an octagon, which is essentially a stop sign, and then another octagon, which is essentially another stop sign. Erase all this. All these are 135, by the way. Another octagon up here, I'm going to erase so we can get it in here. Another octagon. Oh. $135, $135, $135. All these are 135. And I bring one more octagon in. You get the idea, okay? The question is, can I form a 360-degree angle at each of these intersections? Well, 135 and 135 is what? 270. And then if I add a 90-degree angle in, I get 360 degrees the train goes. Okay, 360 degrees. So if you look at it, you'll probably remember, I've seen tile floors tiled like that, right? With octagons and squares, and you put different colors in and so forth and so on. But the key to whether it's going to tessellate a plane is, can I, at a point, be able to come up with 360 degrees? Okay. So it actually can, and that's the reason, because it adds up to two octagons and a square form 360 degrees. How's my pacing? Am I going too fast, too slow, just right? Too fast? Too slow? Just right. Okay, great. Let's take a look at number 3 together. Find the sum of the exterior angles of a regular pentagon. What are the number of diagonals possible in a heptagon? So let's start with pentagon. So it's a regular pentagon. Now, different people define exterior angles differently. I'm going to define it for us in one way, just to make life simple. This is the interior angle, okay? I'm going to call the one on the other side, the reflexive angle that goes with it, the exterior angle, okay? Now, different people define it differently. I'm warning you ahead of time, but that's how I'm going to define it for the purposes of our course, okay? So what I need to do is, because I have this interior angle and this exterior angle, when I add them up, what should I get? Again, we should get 360. What's inside and what's outside actually forms a whole circle, right? So what I need to do is find out what are the angles of a pentagon. It's a 5-sided object. So how many triangles would it be? 3 triangles. And how much for each one? 180 degrees. So we get 0, 40, 540, right? Okay. For the total interior angles of a pentagon, and now we've got 5 angles. So I divide that by 5. And what do I get for the degrees of each angle? You can answer. What's 540 divided by 5? 108. Okay. And so this is 108 degrees. So what does that make this exterior angle if they have to add up to 360? And just subtract, right? Okay. And what do we get? 252. Since it's a regular pentagon, all the angles are going to be exactly the same. So how many 252s do I have? 5 times 252. 1260 is the number. Okay. Did we do exterior angles in class? No. Okay. Am I asking you to apply the ideas we learned? We learned only interior angles in the class. Now I'm asking you questions about exterior angles. Okay. So it's good that you're going to have time to work on it. So hopefully it's not too much of a puzzle, but stretches you a little bit. The second question here is the number of diagonals possible in a heptagon that's 7 sides. So I'm going to draw the vertices here. It doesn't have to be regular. 1, 2, 3, 4, 5, 6, 7. So the easiest way to draw a heptagon is just to put 7 dots on a paper, sort of spread around, and just connect them. 1, 2, 3, 4, 5, 6, 7. Seven-sided object, a little bit funky, a little bit not symmetrical at all, but that's 7 sides. Okay? And I'm looking at the number of diagonals. Well, as we did in class, the goal is to take maybe one vertex and figure out how many vertices come out of that one vertex. So we have a prediction. This is a 7-sided object. How many diagonals should I be able to, suppose I labeled this vertex A. Okay? How many diagonals should I be able to draw at, starting with A? I should be able to draw 4. Let's see if I can do that. 1, 2, 3, 4. Okay? Now I know A is just like B, C, D, all the other letters, right? So they're all going to have the same number of diagonals coming out of them, right? So each one is going to have 4 diagonals coming out of it. And how many vertices are there in this object? 7. So that gives me 28 diagonals. Okay? Did I do that correctly? 7 times 4 is 28. Okay. Now, is that the total number of diagonals in the heptagon? No, why not? Yeah, we count, it ends up counting all the diagonals twice, so we have to divide by 2. So there's actually 14 diagonals possible for a heptagon. Okay? Does that bring back some memories? Great. Number 4. Give your most elegant definition for the following: a ray, a sphere, a chord, a square, a plane, a parallel lines. Okay? Let's try a ray. By the way, you can post any of these answers to the discussion threads and get some credit for extra posting. So take good notes and post your answers to 1, 2, 3, 4, or any parts of them or whatever. Okay? So what's a ray? Well, what's a line? What's a point? Go all the way back to the beginning. What's a point? It's a location. What's a line? Set of points that extend indefinitely in opposite directions, right? So what's a ray?
Subset of a line with one endpoint.
It's a subset of a line with one endpoint. What would be a line segment? It's a subset of a line with 2 endpoints. Okay? What's a sphere? It's a set of points that are equidistant from some central point. Okay? It's a set of points that are equidistant from some central point. Now remember, a circle was that, but that was in 2 dimensions. If we just allow it to be just a set of points equidistant from a particular point, now we're in 3 dimensions. Any direction you can go in 3 dimensions, as long as you go that same distance, that forms the sphere. Okay? A chord. We didn't spend a lot of time on the chord, but it was described in the text. Go ahead.
A line segment where both endpoints are located on a circle.
Yeah, it's a line segment where both endpoints are located on a circle. So if I was to draw a chord, it looks like this. It has one endpoint on one part of the circle, and another endpoint and another part of the circle. What's the largest, and that's not a question here, but what's the largest chord that we can find in a circle? The diameter is the largest one. So all the other ones are shorter, but when I get from this point, I can do all these different chords, but when I go all the way across to the other side, now the diameter, that's the largest chord in a circle. What's a square?
Four-sided figure with equal lines.
A four-sided figure with
90-degree angle. 90-degree angle.
A four-sided object with 90-degree angles. That's elegant. Does it get all the points? Can I draw a four-sided object with 90-degree angles? It's not a square.
Same size.
Okay. It's a regular quadrilateral is one way to say it. Okay, it's a regular quadrilateral with 90-degree angles. That means all the sides are equal and all the angles are equal. So a regular quadrilateral would be the most elegant definition. Yes?
Just going to let you know your computer's going to shut down, so your video's going to stop.
Oh, thanks. Shut down. He went on break. Okay. Square. Also, it's a rectangle that has equal sides. It's another definition of a square. A rectangle with equal sides. So you're right about that. Okay. Also, it's and a rectangle has two sets of parallel lines. So it's actually a parallelogram with 90-degree angles and equal sides. Those are less elegant definitions, but I'm just giving you alternatives. So the most elegant definition of a square is it's a regular quadrilateral. What's a regular triangle called? Equilateral triangle. Okay, perfect. Okay. A plane. What's a plane? It's a set of points that extend indefinitely in opposite directions in two dimensions. Excellent. Okay. Parallel lines.
Two infinite lines that do not intersect.
Well, you don't say infinite lines because they're all infinite, right? Two lines that don't intersect. Do you think that's elegant? Is it sufficient? Could I have two lines that are not parallel and they don't intersect? Will these lines ever intersect? If I continue. So they have to be in the same plane. Okay. Two lines that don't intersect that are in the same plane. Okay. And there's a whole debate about Euclidean geometry and non-Euclidean geometry that sort of rages on this central point, but for now we'll just call it that. Okay. Two lines that don't intersect and are in the same plane. Okay. So obviously they have to be going in the same direction. If they're tilted any way towards each other or away from each other, at some point they're going to intersect. Okay. All right, great. Number 5. A fifth grader defines a circle as the set of all points that are the same distance from a point at the center. Tell what is missing in this definition. What's missing in the definition?
Two dimensions.
Yeah, it has to limit it to 2 dimensions. What has the student actually stumbled upon? The definition of a sphere. Okay. So if he doesn't limit it to 2 dimensions, then it's a sphere. Good try, but he's almost there. All right. Next. How many faces, vertices, and edges does a regular pentagonal prism have? Okay. Well, a prism is made up of a polygon on the top and a polygon on the bottom, and then rectangles connecting them. So the most common rectangular prism that you guys are that all of us are used to is that cube, right? or a box that's really, it's got a rectangle on the top, rectangle on the bottom, and then rectangles all the way around. You could imagine you could put anything at the top, and as long as it's identical with the bottom, and just connect the sides with rectangles, you could have virtually any kind of a prism formed. This one is a pentagonal one, so I'm going to try my best to draw this. So we've got a triangle at the top. We've got a triangle at the bottom. Okay, and then we have sides. So let me see if I can draw the sides. There's a side here. There's a side here, but we're not going to be able to see that. There's a side here in the front. There's a side here in the side. So let me see if I can draw these solidly. Okay, and then we have these dotted ones in the back. So let me see if there's parts of this that you're not going to be able to see, so I'm going to make them dotted. We're not going to be able to see the bottom and the back of that pentagon. We're not going to be able to see these lines in the back. So here's the top, here's the bottom, and here are the sides. There's a pentagon on the top, pentagon at the bottom, and then we've got these lines in the back. Okay, and the question is, how many faces, how many vertices, and how many edges? Well, let's do the faces first. Okay, how many faces does it have on the? It has a top and a bottom, and then how many faces are on the side? There's 5, right? Because there's one face that comes down here, one that comes down here, one that comes down here, one that comes down here, and one that comes in the back. So each one of these lines is the top of a rectangle. So we have the top and the bottom. And we have all 5 sides. Notice this is going to be common in no matter what prism formed from 2 polygons. You're going to have a top and a bottom, and whatever the number of sides of this polygon is going to be the number of rectangles that are on the side. So for example, here we've got a top and a bottom. We've got 1 face, 2 face, 3 face, 4 faces, because there's 4 sides on the square. Okay? So there's going to be 7 faces altogether. Is everybody cool with that? Okay. How many, let me see, faces, vertices? All we have to do is count them, right? Okay. So there's 1, 2, 3, 4, 5. We're halfway done, right? And then there's 6, 7, 8, 9, 10, right? So there's 10 vertices. Are we together there? Is this making sense? 10 vertices. And then how many edges? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 edges. That's with the top and bottom. And then we have 1, 2, 3, 4, 5. We have 5 more edges along the sides. So we've got 15 edges altogether. Okay? So 7, 10, and 5. Now, before we actually end this discussion, because we're going to the next one, notice the pattern here. This was a 5-sided object. and we had 7 faces. How did we get to the 7 faces? We had the top and the bottom and 5 sides. Okay? So without even doing a calculation, if we went to 6 face, if we went to a hexagon at the top and a hexagon at the bottom, can we calculate how many faces there would be? How many faces would there be?
Number of sides plus 2.
So this is going to be for the whatever polygon this is going to be n plus 2. We get n for the number of sides on the polygon, and then we get the top and the bottom. So it's going to be n plus 2 for the number of faces. For the number of vertices, how do we get 10 for the number of vertices? It's all the vertices are at the top and the bottom, right? They're all the way around the first polygon and all the way around the second polygon. So what's this number going to be? There's one for the top, one for the bottom. So what do we get in terms of n? 2 times n, right? So we're going to double the number, whatever the number of vertices in this this polygon. Okay? Now notice what we get here. We have edges. We had 1, 2, 3, 4, 5 for the top. We had 5 for the bottom, and then we had 5 around the outside. So what's this number going to be?
Plus.
2n plus n is 3n, right? Yeah. This is just 3n. Okay? So if I skip to a hexagon, it would be, how many faces would there be in a hexagon? Let's say, yeah, hexagon, 6 sides. How many faces? 8 faces, right? How many vertices? 12. How many edges? 18. Okay? So we can actually work through all these. Now we come down to this question. As soon as I start to see the pattern, now I need the pattern to be able to answer the second question. What was the second question? Another prism has 21 edges. So edges is down here. 3n is the number of edges, right? So we know that it has 21 edges. How many faces does it have? So it's like a puzzle. If I know there's 21 edges, what's n? Does everybody get this? N is going to be 7. So as soon as I know what 7 is n, then it says, how many faces does it have? Well, faces was n plus 2. So 7 plus 2 is 9. So it's going to have 9 faces. Okay, do you see how we did it? What we did is, we took the one example that they gave us, and in solving it, we also figured out sort of a formula for the number of faces. It's the top and the bottom, and then one rectangle for each side, so that's going to give us n plus 2 faces. Okay? Then we counted the vertices, and we noticed the vertices were only in the top and the bottom. We got the one polygon, and then we counted them again for the second polygon, so we ended up with 2n for that. And then the edges, we had all the edges of the first polygon, all the edges of the second polygon, and then the same number added in for the sides, so we ended up with 3n. Okay? Everybody see how we did number 6? Okay. Number 7. Using isometric dot paper, draw a 3-dimensional object corresponding to the following base plan. Okay? Now, if you have trouble drawing, I understand. Okay? Number 1, you want to get in a group with somebody that does draw pretty well. But number 2 is you can actually take this base plan and put it into the virtual manipulatives, right? Okay? So let's see if we can take that base plan and go into virtual manipulatives. So if you go into your Blackboard site and look for virtual manipulatives, under resources. And the manipulative that you want to look at is space blocks. Okay, it's alphabetical, so we do geometry grades 6 through 8, and you can just watch if you'd like, or you can try to keep up with me. Either way. I clear, and I've got one block to start. Okay, I'm going to build that one big tower that's there. So I've got a 3 tower, right? I'm going to. How big is the next tower going to be next to it? 1 unit, and then the next tower is going to be 1 unit. Does everybody see how I'm getting this? Okay. Now I've got to build that. I'm going to put 1 in here. Let me see if I can do this. Okay. I'm going to try to build the second tower real fast. Okay. So here. 3. The problem is these 2 towers are right next to each other. Okay. So this one's a little tricky. Okay. So far we've got 2 towers that sort of just touch at the corners. Okay. They touch at these 2 corners. And then I've got 1 that's sort of there. I can put that one in there. See if I can. It's not helping, is it? Okay. All right. Let's see if I can do it. Send this guy over. I'm going to use my. Oh.
Can you rotate it and then put it on the side?
Ah, yes. Okay. That definitely was the right way to do it. Okay. I'm feeling like I've been drinking. Okay. All right, I've got it. It's sort of like the Titanic on its side. Okay, and now, okay, there we go. And I'm not quite sure how to get this back right again. Let me see if I can turn it and then straighten it up again. Okay. Anyway, now that I've got it straightened out a little bit, I can now go back and remember when we were drawing these, the key was the tops are what? They're like diamonds, right? So you do diamonds, diamond, a diamond here. I can actually put put the diamonds in the top. Then all the vertical lines come down from those diamonds until I hit a ledge. Then I draw a diamond. So every roof looks like a diamond. And then I just fill in the faces. So let's see if I can do it using that isometric dot paper. As I mentioned, the isometric dot paper is on the website. So if you want to just bring it up and draw it, it's not really fancy. It's just there's dots, and then there's new dots that are sort of off center, and then there's the next row, and the next row, and the next row. Let's see if we can do that. Okay, I'm going to do that first top of that one tower. I'm going to put it right here. And it's a triangle, right? Is everybody cool with that? And when you do it sideways or landscape in the drawing, the dots work out better. Okay? And this other one is actually touching right at the corner here. Let me fix these dots up just a little bit. Let me start again. I don't have the isometric, I mean, I could. You know what, I'm gonna actually just, try to, no, I'm gonna just draw it better, okay? 1, 2, 3, 4, 5, 6, and then I'm gonna pull these up a little bit so they're not so tall. Okay, so I start with that first tower, and it's I'll put it right here. That looks a little better, okay? And then this one is right next to it, okay? I looked at my picture and I realized I've got to come straight down for this next line. Going right down the center of this this first line, and I've got sort of 2 rows of lines there. So let me see if I can put this in. Boop, boop. Bit, 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 and all right, so I come down here and draw this line, and this one. I use all the same colors. Okay, this is in here. I can see that. I can see this. And I go down one more layer because there's 2 stories showing on this side. Okay. Okay. Now I've got 2 stories, and then I come out from that. Okay. So instead of, now I'm going to draw a diamond. Okay, and another diamond. So I'm doing the 2 sides, and then I finally have the bottom that I can draw. I come straight down. Oh. Come straight down. Straight down, and then to finish off the front of that face. Okay. So I've got sort of, I've come down the side. I'm going to do the center. I can see 2 stories here in the middle. So I did 1 story. I'm going to do another one. I can see that 2nd story. Now, what do I see at the top of this building right here, this tower? I see a roof, right? Okay, so I'm going to make that into a diamond. Okay. Then I come straight down with that one. Okay. And I come across. I come up. Now I can see the fronts of these 2. Okay. I finish off this building, this little tower in the front. I've got 2 stories back here that I can see. 1, 2. Okay. This is a tower, so I'm going to come down from that tower. I see 1 story here. I see another story here. Okay. And then I've got a roof. And then I finish off that side. Okay? All right. Again, what you want to do is find somebody in your group that's good at drawing it. It works better on the real live paper. I can print out more of them before we go. But what we were doing is taking a vertical projection and then drawing it in 3D. Okay? All right. Next question. And the last one for the practice. Okay? If everybody's worn out at this point. Start with a vertical line and 2 vanishing points and draw the corner of a building with windows and a roof. Okay? So I'm going to do a corner of a building, straight line vertical. It's orthogonal to our plane, so it's drawn straight up and down. Then I've got 2 vanishing points. One here, okay? And I'm going to connect lines to those points. So we get the corner effect of the building. Now we don't have to put all the windows in. We just drew the corner of the building. Oh, it does say windows. We're going to do windows in just a second. Okay. So when I do a window, I have to draw that in perspective as well. So I'm going to do lines that go to the vanishing point. Remember that any of these panes, the actual side of the wall is moving away from us, so it has to be drawn in perspective. The lines that are vertical are actually, we're looking straight at them, so they're drawn straight up and down. And just as the windows get further and further away, you want to draw them closer and closer together so that you have that perspective as well. And then all we have to do is erase this. Erase all the lines drawn for perspective, and you've got the windows of the building, right? And then you can do windows on the other side, same thing. And then all we have to do at this point is draw the illusion of a roof. Okay? And if we were in paint, we would just fill this with whatever color we wanted to do. Okay? So there is the building with windows and a roof on the top. Okay? So, questions at all on the practice? All right. So, my intention, by the way, was to have you guys practice this before you came to class, so it would have went a little smoother if you had seen all these ahead of time, so that we were just reviewing it. But for some of you, this was really great to see it all pull together, hopefully. Let's take a look at the actual project 1, and you're going to see a little bit of more of the same. Okay. Take a look at this first problem. Estimate the measure of the angle formed by the minute and hour hands of a clock of each of the following times. 5 o'clock, that one's easy. 3:30 is actually fairly easy too. 2:06, a little bit of a challenge. 3 is pretty easy. 9:30. So a variety of times during the day, you're going to estimate it by actually calculating just like we did in class. Below is a picture of a billiard table, and let me see if I can go to. Let me go back. Okay. Below is the picture of a billiard pool table. Okay, so if you played pool when you were younger, this is going to help you. I'm going to zoom out a little bit. Use a protractor and trial and error to find out a cue ball should be aimed so that it hits the bottom and right cushion to the side and then strikes the 8 ball that's the black ball. Okay? So the goal here is And let me put the screen up so I can do a little drawing. And let me just do some what ifs, okay? If I start wherever this cue ball is, if I shoot right at this sort of cushion, what's going to happen to the ball? It's going to come right back at me, right? Okay? So that's obviously not what I want to do. Okay? If I went here, it's going to come back, and I want it to hit at least 2 cushions, so this isn't going to work, but that might actually head back towards the 8 ball. Okay? So the first one, it went right to the cushion and came right back. The second one went here, and it sort of flew up in this direction. What do I have to do if I want to actually hit the other cushion? Yeah, I've got to actually aim more over here. And notice as I change this angle, it also changes the angle that the ball comes off. It goes off in that direction. Okay? So what do we notice about the angle? Here, this, I'll give you a hint. When you're shooting here, there's 2 angles that are equal. If I'm going to label them A, B, and C. You tell me which ones you think are equal. A and C are actually equal. Let's do the same one here. Notice A now is kind of small, B is kind of big, C is kind of small again. A and C are always equal. It's actually a principle that we can use from optics, that the angle of incidence is equal to the angle of reflection. Same principle here, that the angle that's coming in, this angle, is the same angle that's coming off. So you can be able to use this to you can use this sort of picture, print it out, and with trial and error and a protractor, you're making the angle that's coming in equal the angle that it's leaving, and try different things. When you hit this, if it flies off here or flies off there, you realize you're off target, and keep twisting it and keep trial and error until you get, the idea is for it to hit here, and then hit this 8 ball. Okay? And in the process, if you've never been a pool player, now you have your first introduction to pool. You might want to go down and try it out sometime. Okay? Anyway, so that's number 2. Number 3. Draw on a grid a polygon that meets all the following conditions. Okay, so what you want to do is maybe take a piece of graph paper or whatever, and here's the description. It's a hexagon. Not all the sides are congruent, so you can't draw anything where all the sides are congruent, and it has exactly 2 acute angles. So notice how I'm taking in the project, we defined what an acute angle was, we defined what a congruent was, but I'm actually applying it. If you go back and we were talking about Bloom's taxonomy, instead of just asking you to repeat the definition to me, I'm actually asking you to apply it to a real life situation. Okay, so so you'll get full credit for that question if you can come up with a polygon that meets those 3 conditions. Okay, 4, real simple. How many squares are in the following design? Okay, so all you have to do is count up all the squares. Remember when we were doing the diagonals, remember that whenever I get sort of a fairly complicated problem, I have to come up with a system, a systematic way of counting things so I don't miss any. Okay, so as a team, you might want to work on that, come up with a systematic way of counting those squares. Okay. The next question is, go to the following website, and this is, it's basically the tessellations website. Let me see if this one works. I might have to fix this link if it doesn't. I think it does. We'll see. Try a new. Okay, it doesn't. On the Virtual Manipulatives website, you're going to look at geometry 6 through 8, tessellations. That might be a slightly old link. Okay, and what your job is to take this and take these objects. We did one earlier where we had a octagon, another octagon, another one, another one, and then we found a square, and we found that it tessellated. Okay, so the goal is for this one is to build 5 different patterns that tessellate a whole plane. When completed, print each pattern. Let me just go here. When we're here, notice if I wanted to print this screen, by the way, I can zoom out, by the way, if I'm building a pattern and I want to repeat it. And here's another trick. If I copy this, Control C, and paste, well, if I copy this, or I can actually clone this and bring it back again and clone it again. So I highlighted it and then I cloned it. So I can bring these pieces, and I can zoom out and bring these pieces together. Zoom again out. And I can build the patterns over and over again and tessellate a plane. Okay? So the point here is this, to clone it again. So if I want to highlight this and clone it, highlight, clone. So the goal is to build 5 of these using the objects that are here. Okay, some are going to tessellate. Well, I think virtually all these are going to tessellate. And the goal is to make it pretty, to actually use your imagination to make it cool looking if you want to. I mean, it doesn't have to be, but it would be nice if it was a cool looking object. Okay, so you're going to come up. So put the person in your group who's the most creative on that project. Okay. 6, using isometric dot paper, draw the 3-dimensional object corresponding to the following base plans. So you're going to take those base plans and turn them into real live objects. Okay. And then 7, long before panini was the name of a sandwich, there was an artist by the same name. Consider 2 paintings, the 2 paintings referenced below, and label the vanishing point and describe the effect of the light sources on the shadows. Okay, so let me see if I can copy these and go here. And so you might have to do a little searching on this one. Let me see if I have the links. What you're looking for is the architecture caprice with Pantheon and Colosseum and the Forum of Trajan. So if you actually just put this into Google and find it, I think that link is, they always change the links on me, so those links may be no good anymore. But if I go to Google and I type in that description and go to images, I should be able to find that image and let me see. You know what I'll do is I should just paste that. What I'll do is I'll paste this into the website so you don't have to find it. Okay. So it's actually this one. And I'll post that to the website so you have it. So on those last two, they're going to be objects, and what you have to do is tell me where the vanishing point is and what the shadows are like. Okay? Now, a couple of things I just want to tell you before I sort of let you break into groups today. Okay? At this. I want you guys to be smart. Okay? So you can work in your group. If your group gets stuck on something, okay, one strategy you definitely could use is suppose if this is actual project that you're going to get graded on, right? So if you're stuck on like number 1, it's illegal, against the rules, for you to say, how do you do number 1 on discussion threads, right? Everybody's agreed with that, okay? But if I look on the practice and see one that's similar, I can ask anything I want to about practice 1, okay? So I might go back and say, somebody explain to me how he did that 420 thing again. That's a legitimate question, and then you can take whatever you learned from that and now apply it to the new situation, okay? So anything you saw, for example, we get down here and we're looking at the base plans and how to draw them, okay? You can ask a question about how we did the one that we did in class and ask advice about that, and then use that information to apply it to this. But everybody heard me say that it's not fair game for you to say, how do you do project 1, problem number 6? Okay, that's not cool. All right, let me go over the ground rules real quickly again. I want to make sure we're all on the same page. Okay, number 1. When's this due? Monday. How many documents are you going to hand in for your whole group? 1 document for your group. How big can the groups be? Up to 4. Can I work by myself? Yes. Why would you? But you could, okay? If you're working in 2s, does the person that's working in a 2-some have to do twice as much work as somebody in a 4-some? Yes, probably, okay? Because you have half the number of people working on the project, okay? So it's to your advantage to have a 4-some, but I understand some of you may not really enjoy working in big groups that much, okay? So it's due on Monday. You can word process it. You can put drawings in. Just put it all together into one document. You can post anything you'd like on discussion threads on practice 1. Post some of your notes from today. Post any general questions, but you can't post questions like, how do you do number 5? Okay? Any questions at all? Today, you can start working on project 1. I'm going to give you a copy of each. I'm going to give each one of you a copy of it. And you can work on it as long as you want to this afternoon. So if you want to say, like one group says, you do number 1, you do number 2, you do number 3, and let's get out of here. Okay? I'm not going to look at you cross-eyed when you leave. It's due when it's due. You are adults. You can handle it any way you'd like it. Other groups, so you get from that extreme, everybody just gets the problems and let's go, and we'll work on it. 2, some people might want to just finish the project today before you leave, okay? And everything in between, all right? Any questions at all for project 1? Okay, all right. Let me give it out to you, and you guys can get started on project 1.
Thank you.
I'm going to print out some extra isometric documents. You can have something.
Do you want me to stop today?
That's okay, you're very prepared.